Yeah, okay. So welcome back, everyone. I'm pleased to announce the final session for PDC 2021. During the next roughly 90 minutes, we will be talking about the energy mix of tomorrow, future fuels in the pipeline. It is a great pleasure that we have been able to win Barbara Jinks as session chair. She has over 35 years in the gas industry, from greenfield pipeline projects to international corporate roles. Her academic training in engineering and law and experience across most parts of the gas industry has prepared her well in her current role with the intergovernmental organization Irena, the International Renewable Energy Agency, where she looks after the topic of greening the gas sector with a focus on the use of the gas grid to deliver biomethane and hydrogen. Barbara is also a member of our PDC Advisory Committee, and I'm very much looking forward to your panel discussion right now. So please, Barbara, the floor is yours.
Good morning. Thank you, Dennis, for that introduction. And it is my pleasure to be here. I think the last time I was here, I was in a different function in the gas industry, but I'm very happy to be with Irena now, because Irena is really looking at the role of green gases and the role of the gas sector in decarbonization. And I believe, along with Irena, that all forms of renewable energy are essential to reach decarbonization, and a fair portion of that comes from renewable gases, or renewable energy in the form of gases, and that's what we'll talk about today. Irena looks at all forms of renewable energy, which is wind, solar, hydro, geothermal, and ocean, tide, and wave, and current. And every year it issues an outlook, and on Tuesday the veto was issued at the German Energy Transition Dialogue in Berlin, the Transition Dialogue, and that stands for the World Energy Transitions Outlook, and it's available on the website of Irena. All Irena website reports are available on the website. And basically the veto tells us, the outlook tells us, that to reach minus 1.5 degrees C, we have to absolutely change the way we use and produce energy, and we all know that. Irena believes that 90% of the end consumption of energy by 2050 can be from renewable sources. And that includes bioenergy and renewable electricity. But only 51% of end uses can be electrified. So we still have 49% of end energy consumption at the end user point that cannot be electrified. Bioenergy can account for 18% of end consumption, and natural gas is still needed, but only at 4% of end consumption. And that means natural gas goes down to 25% of its current quantities of 2008 figures. Coal goes down to 2% of end energy, and oil is 4%. So there's a radical change. And one of the ways of delivering renewable energy to the end user, if we cannot electrify that pathway, is by hydrogen. So it's by gas. And as we know, hydrogen can be made from reforming natural gas or from renewable energy electrolysis, splitting water to create green hydrogen. And of course, Irena promotes green hydrogen as being the cleanest cleanest process to have the end point with hydrogen. Irena estimates that 12% of final energy consumption is in the form of hydrogen. And of course, it's limited by the amount of energy from the windmills and solar panels and hydro and geothermal. But 2/3 of that can be green, and 1/3 is blue hydrogen. And we need the blue hydrogen for the quantities. And it will be cost competitive at 2030. So it's a really good story. I don't think hydrogen's a hype. I think it's a momentum. And our task is to catch that momentum and make it something valuable. So today's panel really reflects the fact that necessity is the mother of invention. And we see many projects that look at how do we transport hydrogen effectively and affordably. And today we'll hear about new developments in producing hydrogen, and in terms of blue hydrogen, the CCS. What do we do with the CCS? We'll hear from Equinor on that, and then we hear from Baker Hughes and Siemens on technical aspects of blending hydrogen or 100% hydrogen in the gas grid, that's storage and pipelines. And we'll look at some of the developments of the major pieces of kit on the pipelines and storage facilities in compression and valves. So it is my pleasure. I will introduce the three panelists, and then we'll listen to the three panelists in a row without interruptions. And then myself and the three panelists will come back to answer questions and discuss the issues in a bit more detail. So it is my pleasure to welcome Steinar, Luca, and Peter as our panelists. First, Steinar Eikaas will speak. He is the Vice President of Low Carbon Solutions in Equinor in Norway. He enjoys his job. He works for an oil and gas company, but he's part of the solution of promoting low carbon solutions. And we need that. We really need the oil and gas industry to use its skill and funding to help us solve these problems of decarbonization. Steinar is confident that we need to build on the existing infrastructure and adapt it to the new reality. And he's the Vice President of Low Carbon Solutions, and he heads up that in Equinor, and he's responsible for carbon capture and storage, CCS, and hydrogen. So I think he has a very exciting role. Equinor is involved in low carbon projects ranging from open source, flexible CCS transport and storage, pre-combustion of hydrogen projects within the CCS, and for all major energy sectors, as well as the traditional post-combustion carbon capture. Second, we'll hear from Luca. Luca Maria Rossi is the Vice President Commercial of New Frontiers for Baker Hughes. Again, another exciting job title. Luca loves his job because it allows him to explore new frontiers and find new technologies. And he feels that green gases are at the center of the solution of global warming, and they enable quicker and more effective infrastructure upgrade. And I know that we all agree with that. He began his career with GE in '97, and he's now the Vice President of Technology within the Turbo Machinery and Process Solutions business unit at Baker Hughes, which is a GE company. He's currently responsible for all aspects of technology development. So no pressure, Luca. Responsible for bringing new technology to the market, along with fulfilling customers' commitments and needs. And then last but certainly not least, we have Peter Adam, who will speak to us here in Germany from Siemens Energy, and he's the head of the hydrogen business unit. Peter's also very excited to be part of the business into a new decarbonized energy world, and he feels that hydrogen is one of the key levers to decarbonize. But we need to explore both blue and green extensively to reach our targets, and I absolutely agree with that. He also believes that technology is basically available, but the regulatory and the commercial preconditions need to be established, and that's absolutely true. He's been with Siemens since 1981, as it started as an electrical engineer, worked in Germany, but also on China, Iran, and United Arab Emirates projects in account management strategy, project and market development. And he's now in the oil and gas group in hydrogen, and he's now been there for 2 years. So you can see that we're privileged to have three panelists that really are passionate about what they do. And they're actually, I would say, they're leaders in their areas and well-known companies. And we really look forward to listening to them. So now we'll listen to the three presentations, and I'll join you with the panelists at the end. Thank you.
Yes, so I'm Steinar Eikaas, and I'm responsible for business development within low carbon solutions in Equinor. And we define low carbon solutions as CCS and hydrogen solutions. So what I will do today is to walk you through our initiatives. And what I will do is to start with just an overview of why we need low carbon solutions alongside renewable solutions. And the way we approach this is that when we look at the entire energy system, it is a system of what we define as easy to decarbonize sectors, and then there are some that are really hard. Kind of the fact is that renewable solutions like solar, wind, and battery solutions are actually perfect to decarbonize the easy part of the energy system. And one example for this is like the battery electric vehicle, which is actually superior to actually many fossil-based vehicles today. But at the other end of the scale, you have much heavier systems, and for instance, within the transport sector, if you look into the shipping sector, long-haul transport by sea, you will only get a few hours if you fill up a cruise ship with batteries, almost until it sinks. It doesn't really help much. But on liquid hydrogen, ships may go for a month on one tank. And the same is the fact for production of electricity. The cheapest form of electricity today comes from renewable, solar and wind. But that's only the case when the sun shines and when the wind blows. But we also need power when that is not the case. Today, that is supplied from natural gas. And in the future, we can do so without any CO2 emissions if we burn hydrogen to produce flexible power. And then within industry, there are some industries that require very high amounts, large amounts of energy, and also stable 24/7 supply. Again, not possible to achieve from renewable sources. And this is also where we can use hydrogen in the future. And if the hydrogen is produced either green or blue, it will be without a CO2 footprint. And the hardest sector of them all to decarbonize is what we call the heating sector, where you need huge amounts of energy storage. Today, it is supplied by natural gas, and in the future, we can offer the same flexibility and large-scale storage by hydrogen solutions. So in Equinor, we have basically fully embraced the renewable solutions, and we are heavily involved in offshore wind. But also we see the limitations of these, and that's why we are pursuing low carbon solutions to basically decarbonize the difficult part of the energy system. And by pursuing both, we can basically decarbonize from both corners of this energy system. So what I will do now is to walk you through some of our initiatives. This is an overview that you have in front of you of what we are involved in. Some of this is CCS related, but as you know, CCS is like a prerequisite for blue hydrogen, so it's also important in a hydrogen setting. So we are involved in everything from a traditional post-combustion CCS in the Teesside project, together with BP, Shell, Total, and Eni. We are planning here to install a gas-fired power plant with capture of CO2, which will make this carbon neutral and be able to respond and back up wind farms with flexible power. And then within the CCS value chain, we also have what we call the Northern Lights project. This is innovative in the sense that it's the first time CO2 is captured in one location and then transported and stored in another location. And we make that possible through the introduction of a shipping-based solution. And these ships will start collecting CO2 in the eastern part of Norway and ship them to the western coast, where it will be permanently stored offshore, 3,000 meters below the seabed. Of course, these ships are not restricted to only transport CO2 within Norway. We can go to any harbor in Europe, basically, and collect CO2. And we will introduce here a solution for industries in Europe, which has the ambition to manage their CO2 emissions, but don't have a storage solution today. From now on, they only need to capture the CO2, and then we can come and collect the CO2 at the harbor. We're also involved in a CCS value chain in the UK called the Northern Endurance Partnership, together with the BP and National Grid. This is not a ship-based solution, but as a pipeline CO2 solution. And the aim is to transport CO2 from two large industrial clusters in the UK, the Teesside and Humberside clusters, and store the CO2 offshore UK in the Endurance reservoir. And then we are also mapping the North Sea for additional CO2 storage, because we see that there will be a large need for this service in the future when Europe is going to decarbonize its economy. And then moving on to the hydrogen part of the portfolio, we have divided this into 3 clusters, one in Norway, one in UK, and one in Northwest Europe, which basically is the Netherlands and Germany. So in Norway, we are focusing very much on the maritime sector. We see hydrogen, and then in particular liquid hydrogen, as the solution for those ships that sail distances beyond what is possible to cover with battery solutions. And then we are also believing in ammonia solutions, and part of a concept up in the far north, where we look at the production of blue ammonia. In the UK, we have for years kind of developed visions of how natural gas can be replaced by hydrogen. We did so with this H21 North of England concept 2 years ago, where we demonstrated how it would be possible to decarbonize the heating sector by replacing natural gas with hydrogen. In the short term, we are working in the Humber region, and I will talk more about that shortly. A very exciting concept for application of hydrogen within the largest industrial cluster in UK. And then in Germany, we are working together with ThyssenKrupp, who has one of Europe's largest steel facilities, manufacturing steel. Today, they use coal to basically reduce the oxygen out of the iron. In the future, they may be able to use hydrogen, and we are working together with them with the role of supplying clean hydrogen to their process. We're also working in Northwest Europe with the flexible power concept in Netherlands, looking at an existing power plant to see if it can be repurposed to burn hydrogen instead of natural gas. And then finally, also very heavily involved in green hydrogen, a consortium together with Shell, Gasunie, and RWE called the North H2. And the intention here is to build a dedicated wind farm, produce renewable electricity, and then convert this electricity into green hydrogen. This is a very significant large-scale concept, which really will kind of be the same ballpark scale as the blue hydrogen concept. And we strongly believe that we need to build scale early to basically lift up a hydrogen value chain. And moving a little bit into more details on some of the projects that we are involved in. What you see ahead of you is what we probably will sanction as the first hydrogen project in Equinor. And this is not only hydrogen, this is liquid hydrogen. And we're developing this together with the BKK and Air Liquide in Norway. The intention is that we will produce first green hydrogen, taking electricity from the clean grid in Norway, which is mostly supplied with hydroelectric renewable power. And then after producing green hydrogen, we will liquefy it, and then we will use the liquid hydrogen as batteries on board ships, like you see in the background. So 2 of these ships are planned to be built. Liquid hydrogen will serve as a battery, and then hydrogen will go through fuel cells, and these ships will be fully electrically propelled. The role of Equinor here is twofold, not only to produce the liquid hydrogen, but also as a customer of this, because today we transport large amounts of cargo between our offshore bases, and we do this by road today. And we will see if we can shift this transport from road to sea, and by doing so, use our purchasing power to facilitate a market for these ships to be able to operate as cargo vessels on sea without any CO2 emissions. And then moving back to Humber, which I was talking previously about. We have now developed and submitted an application for a hydrogen demonstrator in the Humber side. of 600 megawatt blue hydrogen production with a dedicated CCS solution towards endurance. And the aim here is that this hydrogen, which will be clean, will form the basis of a 30% mix into a local power plant, and the remaining 70% will still be natural gas. This will reduce the CO2 emissions by close to 1 million tons. And then we have as next steps in this region to expand hydrogen production to enable 100% flexible power generation from hydrogen. We also look at supplying local industry, including steel, with hydrogen. And in this cluster, we also have a power plant, which is today burning biomass imported from the US and Canada. And this CO2, which is the result after it has been burned and produced power, is considered to be carbon neutral. And we will also look into capturing that CO2. And if we store it, it will count as negative emissions. And if we utilize it together with clean hydrogen, we can basically produce artificial fuels without any CO2 footprint. So a lot of exciting stuff going on in the UK for the moment. And finally, some words about what we can do in Norway. Today we are exporting almost all our natural gas into Europe. And of course, that natural gas can be converted to hydrogen, as I just explained. But we will also look into converting it to hydrogen before we export it. And then we can export it as mainly blue hydrogen. And by building this blue hydrogen value chain, we can, over time, gradually phase in more and more green hydrogen as we develop, for instance, offshore wind production. The beauty of doing this in Norway and potentially building a new pipeline is that we can connect this pipeline into what we consider to be the hub of hydrogen in Europe. And today it looks like the Groningen area in the Netherlands probably will have such a role. It used to be Europe's largest gas field, and it is expected to be almost closed down by the end of this decade. That will free up a lot of infrastructure today carrying natural gas. In the future, it may carry hydrogen. And if that is going to be the case, that's something we can connect to from Norway and be part of this system as a supply chain. So there's a lot of exciting stuff going on in hydrogen. We believe that building on the existing natural gas infrastructure is the way to start. To convert this to hydrogen, we need large scale. And we can get large scale early by introducing blue hydrogen. And then when we have done that, we can phase in more and more green. And then as an end game, we believe green will be the solution for the future. But it's going to be several decades before we are there. In the meantime, it's very important that we can lift this based on clean blue hydrogen based on natural gas with CCS. So I think I'll stop there. And yes, that's it for now.
Good morning, everyone. First of all, I would like to thank the organization of this event for this invite. It's a very prestigious stage where to talk from. So thank you very much for having me and my company represented here. As a first thing, I would like to introduce myself. My name is Luca Rossi, and I am the Vice President New Frontiers for Baker Hughes. Vice President New Frontiers means that I'm helping my company to explore the technology, the solution that are not in use today, and in particular exploring what is needed to face and to find opportunities in the new energy transition world, coping with the new energy mix that will come from the commitment that the world is taking to reduce global warming. Now, like you can imagine, it's in my job, I came into the job with the concern for an oil and gas company that there may be a big threat for us in this energy transition, while I'm getting more and more convinced that the oil and gas industries will have a lot of opportunities coming from that presentation, from that situation. And starting from Baker Hughes, I would like to shortly introduce what is our company doing in this field. Baker Hughes, it's a very old name in the industry. It's a very old historical oil field service company, but the new Baker Hughes is a very young company. It started 3 years ago from the merger of the Oil and Gas division and the Baker Hughes company. Now, the Oil and Gas division also included some historical brands that were working in the pipeline world, like the No Opinione brand for gas turbine compressor, the PII brand for inspection, and all the solution around emission control. So our company took a big step, and we took a very big commitment in terms of net zero carbon commitment, to be 50% of emission by 2030 and net zero by 2050, because it's clear that if we want to really contribute to create a better world in terms of energy mix, we need to start looking at ourselves on reducing our consumption and our emission. Now, going to the specific discussion for today on the fuels, I would like to focus on two things. Of course, I would like to focus on hydrogen, which to me is the best candidate fuel to support the energy transition, energy mix goals. And talking about hydrogen, the history of Baker Hughes through the brand I mentioned before is very long. Hydrogen, it's a gas that has been in the market for many years, produced in refineries and for industrial application. And we have a long experience. We have compressors that can handle hydrogen, several compressors in refineries. We understand the material to handling and transport hydrogen. And in particular, and that would be one of the topic for my drill down, we have a wide capabilities to use hydrogen in our turbines. On the right side of the chart, you see the complete range of our offering on gas turbine. Not all of them will apply to pipeline, but for all of them, we have a plan together with our partner General Electric to make them able to burn very big quantity of hydrogen. For today's discussion, being focused on the pipeline, I would like to spend a little bit of time on the new product line that we are introducing in the market, the novelty families. We are coming to the market with 3 models, but in particular, 2 of those, Novelty 12 and Novelty 16, are really designed for pipeline application. As you may see, we are starting this unit already with very state-of-the-art emission data on NOx, on CO. But we are also making them capable of or start up a burning gas blend up to 100%. We are creating a system around these turbines that will be able to follow the industry evolution from 100% natural gas to 100% hydrogen in steps. And we are designing a system that can easily carry 10-20% hydrogen, and we are advancing the technology to go up to 100%. Without compromise with the maintenance needs and clearly the simplicity of operation that is the characteristic of this turbine. In this respect, I would like to talk a little bit about an experience we had with one of the most historical pipeline company in Europe, which is NAM. I know that there would be a dedicated paper to this experience in another section of the symposium, but as NAM and Baker Hughes test for the world's first hydrogen blend turbine, we actually took an actual product that is going to go in an actual NAM project, and we tested for higher blends of hydrogen, up to 10%. And the meaning of this test goes above the result of itself. It's the commitment that both NAM and Baker Hughes are showing in regards of cleaner fuels, and getting together, instead of doing a separated development, allow for Baker Hughes to partner with a major operator, and for NAM to get access to a very important technology provider. That made this development not a lab one, but a real life example that is proven on the field and that can be applied very, very easily to other projects. In particular, clearly, we have also a lab dimension for that, which is the combustion system. We all know that the biggest difficulties for hydrogen would be in the combustion physics, but of course we are also looking at the package and auxiliary design and operability. In order to cope with this problem, what we did, we set up a dedicated combustion test facility. It's in Sesta, Italy, in Tuscany. And basically, we use that in conjunction with the virtual lab test and to prove on a full-scale mode the combustor we will use for hydrogen. And also, we are set up a dedicated line of additive manufacturing in order to fast prototyping and to very quickly prove our technologies. Having said that, I was reflecting with my team on why we are doing that. Clearly, our goal is to help new fuels to develop. It's something that can only happen in common and in combination, in partnership with all the operators, with all the industries. But the opportunity is very big. I try to make a simplification. We have, as Baker Hughes, approximately 100 LM2500 gas turbine driving compressor in the pipelines application. If we will be able to burn 30% hydrogen in each one of those, it's like taking 300,000 passenger cars every day out of the street. And this is a very small section of all the fleet that we have in the pipeline world and all the fleet that everybody has it. So you may imagine how big a contribution. It's like stopping all the cars of a medium city like Florence. So very big opportunity. And that makes me get to the closing on my presentation, because the reflection that I would like to bring is that we as Baker Hughes are very committed to help the world reach its decarbonization targets. It is very clear while we develop our product and our solution that we can only do in partnership with the rest of the industry. At the same time, if we get together as an industry and we apply the technology, the solution, and the commitment we are, I think we can really move the needle and help the world reaching the very important target of reducing global warming. And with that, I thank you for the attention, and I will be on the panel to get Q&A from your side. Thank you very much.
Good morning. My name is Peter Adam. I'm working with Siemens Energy, and I'm responsible for business development and marketing of hydrogen and sustainable business. And of course, hydrogen pipelines is one very important factor. Basically, hydrogen infrastructure is an enabler for the carbon neutral energy system, what I want to talk about now. First, I want to address a little bit the overall hydrogen economy as it is, with a focus on midstream pipelines and storage. So there's a lot of discussion about hydrogen blending, basically mixing hydrogen with natural gas into the pipelines. Technically, it's feasible even using existing equipment up to 40% with some adaptations. But it seems to be that the users do not really like mixtures of methane and hydrogen. Hence, it's more likely that we only see very limited mixture and blending of hydrogen and natural gas in pipelines, but we'll see a separate hydrogen pipeline network to the existing natural gas network, repurposing existing pipelines. Transportation of hydrogen in pipelines is energy intensive and difficult. I come later to this, and therefore I think those pipelines will typically shorter than 1,000 kilometers. Of course, today, nearly all the hydrogen, 75 MTPA, is produced in steam reformers or ATRs, and by doing so, roughly 750 million tons of CO2 is emitted. Now, upcoming is electrolysis technology, where hydrogen is produced out of renewable energy. But there is a major obstacle, because to make 1 ton of hydrogen with electrical energy, you need 55 megawatt hours. And of course, when it comes to pipeline and infrastructure, it's also storage applications for hydrogen. Basically, we have already several salt cavern storage applications for hydrogen on this planet. Not in Germany, but in the US and in the UK. And therefore, it's proven that salt caverns can be used for hydrogen storage up to 300 bar. and therefore the infrastructure can also be used that we have here extensively in Germany. Next page, basically, I want to explain a little bit about blue versus green hydrogen. I repeat myself, 75 MTPA is produced today. More than half of it is used to make ammonia, and then out of ammonia, mainly urea as fertilizers. 33% go into refinery for desulfurization of fuel, and maybe most of the balance goes into methanol production. And normally the hydrogen is produced basically where it's used. Also, we have some existing hydrogen pipelines already, small diameter, low flow in North America and in Europe. When we forecast that the production of hydrogen may increase 10 times until 2050, it's very clear to do this with electrical energy only, with green hydrogen, you would need more than 40,000 terawatt hours, equivalent to the output of 15,000 wind parks, 1 gigawatt each. Therefore, it's clear to everybody to build up this infrastructure takes a long time. Therefore, it can be assumed that even in 2050, a substantial amount of the hydrogen still comes from natural gas, as in blue hydrogen. And technologies to decarbonize the hydrogen production are available and just need to be applied. And at the end, if you make a molecule of hydrogen in a steam reformer and all the CO2 is extracted and stored, I think a molecule of blue hydrogen is as green because it has no CO2 emissions. Okay, then coming back to the equipment required for hydrogen infrastructure like pipelines and storage equipment. Here you see basically a complicated map of all the applications we have already. Because I repeat myself, hydrogen is used in industry since decades. Hydrogen is pumped mainly with reciprocating compressors today. We have existing pipelines for hydrogen, also low flow, comparable to natural gas pipelines as well, mainly using turbo compressors. We have available already gas turbines that can run with hydrogen fuel up to more than 60%. And we have, of course, all the technology required to capture the CO2, pump the CO2, inject the CO2 as well. You need compressors or pumps. And we have also high flow, hydrogen-rich syngas applications in various petrochemical facilities. So basically, you can say all the equipment required for hydrogen infrastructure and pipelines and storage is available, except high flow turbo compressors for hydrogen as a point here, and I come to this later. Before we continue this, we need to talk a little bit about the difficulties to pump hydrogen. Hydrogen with a low mole weight of 2 is basically the most difficult gas to compress, in particular in turbo compressor and the way how they operate. Hence, basically all the hydrogen today is pumped with reciprocating compressors. Reciprocating compressors, by the nature of their working, have 15 to 20% better energy efficiency than turbo compressors. And studies with pipeline companies show that up to a volume flow of 750,000 norm cubic meter per hour with 3 parallel units, what is equivalent to the output of a more than 2 gigawatt electrolysis system, reciprocating compressors can be economically applied. Of course, for higher volume flows, and we see already inquiries in this direction in the planning for very large hydrogen systems, we need turbo compressors. In order to have turbo compressors where in a single casing the typical delta P of a pipeline compressor station can be bridged, new impeller technology need to be developed where the tip speed of the impellers is higher than 700 meters per second. This has certain challenges in the materials and the high centrifugal forces, but developments are ongoing, and I'm very sure that before we ever have to pump more than 750,000 norm cubic meters, those compressors will be available, and we will be able to offer equipment where in a single casing with maybe 4 impellers, I'm not sure yet exactly what output is, the pipeline operators can bridge the typical delta P you have in a compressor station. In this picture, what probably many of you know already, you see the map of the plan of the European long-distance pipeline operators of the so-called European hydrogen backbone pipelines. It's quite extensive. More than 75% of those pipelines will be repurposed natural gas pipelines and only 25% new build. And the first studies undertaken show when you repurpose existing natural gas pipeline to hydrogen, the investment cost is only 10 to 15% of a new build. So basically, it could be done with reasonable investment, relatively short term. A hydrogen pipeline has roughly 90% of the energy transportation capacity of a comparable natural gas pipeline. Also, it requires substantially higher compression power to do this. But we also need to keep in mind at the beginning, when certain pipelines are repurposed for hydrogen, they may not be utilized with their full capacity. And if maybe the capacity in a pipe is only 10, 20% of the maximum, the required compression power is pretty low, and you can bridge very long distances with a single compressor station at the beginning. What then, when the flow increases, get vice versa, and you need more compression powers than in natural gas. Again, we can serve this compression requirement with recipe compressors up to a certain volume flow, and above this, we need turbo compressors that are under development. For storage applications, we have already compressors existing that can pump hydrogen up to 300 bar in salt cavern storage applications, and already certain pilots here in Europe, both for pipelines and storage, are under consideration. When we talk a little bit about what need to be done to enable hydrogen flow in pipelines from a rotating equipment point of view, we can say when you have an existing pipeline and you blend, as long as the hydrogen content in the flow of the pipeline is less than 10%, basically for the rotating equipment, no changes are required. They lose a little bit of their performance. And of course, maybe you need to do some new approvals on the checking on the safety guarantees, but from the rotating part and performance, it can work as it is. When the mixture in the hydrogen goes up to 40%, you can change the inner bundle of the compressor to enable a certain efficiency for the mixed flow. And it's fair to assume that most of the gas turbines you typically have installed in a pipeline can already use hydrogen fuel to a certain percentage, or can be respectively upgraded to do so. But when you increase the hydrogen content above 40%, you need new compression equipment. And we talked about this as well, what that means. Again, due to what I see at the moment, that the pipeline operator tend to say, I will have separate network. I do not see very much blending happen, but we still may see something of it. And then we have basically the infrastructure established between dedicated hydrogen and natural gas pipelines. Of course, the equipment is available. Here you see the picture of a large recipe compressors for hydrogen application. There are plenty of references in this available from us and other suppliers. So basically, it's a very well-proven technology. I know, of course, that the European pipeline operator, for whatever historic reason, have not many recipe compressors in operation and have not much operational experience. But this technology is very well proven and widely used in North America. So it's basically available. And if someone needs hydrogen compression today, that is a choice he needs to have. Of course, we have today already recipe compressors for hydrogen up to very hydrogen-rich components, so-called syngas compressors in petrochemical processes. But in order to achieve reasonable compression ratio, maybe from 50 to 90 bar in a pipeline, we would need 3 casings with more than 20 impellers, and respective technology is developed to put this all in a single casing, as the pipeline companies need to have. Last and not least, I want to talk about the gas turbine drivers that are installed or can be installing in gas turbines. You see in this picture the current hydrogen fuel capabilities of the Siemens Energy gas turbine fleet. And in particular, for those gas turbines that are usual for pipeline transportation, some very substantial hydrogen content is already available. We are currently commissioning engines with gas turbine fuel in Brazil up to 60% with DLE burners. And it's fair to assume that in a very few years, the typical megawatt range of gas turbines for pipeline operation can be fueled with 100% hydrogen. We from Siemens side then prefer to do this so-called dry low emission burners, where we keep the NOx emissions in the gas turbines under control with dry low emission technology. Although already today, the so-called wet low emission technology is available, mainly used for aeroderivative gas turbines, where you inject water into the gas turbine in order to keep the NOx emissions under control. But to give you an example, for a 35 megawatt aeroderivative gas turbine, you would need roughly 15 ton of demineralized water to keep the NOx level what we have here in Europe. Therefore, it's perceived by many customers not as a viable option. So again, in a few years, I would say 2-3 years, the typical megawatt range for pipeline gas turbines will be available with very high, up to 100% hydrogen fuel capabilities. Okay, that's the end of what I want to share with you today. I hope it contributes to the conference. Thank you very much.
So welcome back, everyone. I hope you enjoyed the 3 presentations, and it is my pleasure to welcome Peter, Steinar and Luca to the discussion room, where we'll have a chat about some of the key issues and also answer questions from the audience. So actually, we have a first question from the audience. Roger Vogel is asking Peter, what are the biggest challenges and risks in Europe in keeping to the schedule and in terms of safety? Now, I presume he's talking about, Peter, you were talking about hydrogen in the pipeline, so maybe we'll focus on hydrogen for that. Thanks, Peter.
I don't see a very big risk. The studies we have supported so far with pipeline companies indicate that using existing pipes from natural gas to be converted to hydrogen seems to be not a very big issue. So all the talks we had on hydrogen embrittlement and so on seems to be less risky as it is. Of course, safety assessment needs to be done. Basically, most equipment can be upgraded or is available. So in my opinion, the challenge is not technical. Of course, we have to overcome some. It's more economic. At the end, it means, is there in the near future sufficient hydrogen available that really it makes sense to fill a pipe? And is it economic for operator to change?
I agree. Irena is doing a deep dive into the technical and the cost aspect of transporting hydrogen in the existing gas grid, and there are no technical barriers. There are challenges that we have to overcome, and we have to tweak things and modify things. But it's regulatory and commercial and cost. Maybe I'll start with Steinar, because Steinar, you were the first to talk. So congratulations on the range of projects that Equinor is undertaking, and for saying in your talk that green hydrogen is the end game. That absolutely fits with the Irena projections. Can you tell me a little bit more about what role you see a company like Equinor has in this overall challenge for climate change, or to decarbonize energy in particular?
We believe we have several kind of levers to pull where we can contribute significantly and be part of the solution. And today we are we're most known for being an oil and gas company, but actually we are very large also in offshore wind, and we have under development the world's largest offshore wind farm, the Doggerbank, and we have several in operation already in the UK and Scotland. But I think where we can really move the needle is to basically take the existing oil and gas value chain and make it compliant with a zero carbon future. And of course, blue hydrogen is one of those solutions where we really make an effort, like you have seen in the presentation. And this also, of course, has the important element of CCS, where we already have sanctioned the Longship or Northern Lights project, which in itself is a major milestone in the CCS business, but also important because it creates an important foundation for blue hydrogen. So kind of to launch the blue hydrogen projects from now on will be much easier because we know that we have a CCS solution for them.
Yeah. And I invite all panelists to jump in if at any point you want to discuss about issues. And maybe one of the issues is actually the role of your own companies in lowering their own footprints, not just the footprint of the equipment that you produce or use. Very quickly, Steinar, why do you not mention pyrolysis, which is blue hydrogen, but you don't have CO2, you don't have the hassle of CO2? Assuming the cost can come down, if that's your first.
So it is a cost issue, and it's also kind of efficiency issue, because what you get with pyrolysis is less hydrogen compared to steam reforming. And for us, it is important that we get kind of the maximum amount of energy out of natural gas. To basically, it has to do, of course, with the commercial part, but also I think the disadvantage of blue hydrogen is, as you say, the CO2 and kind of a firm carbon is maybe an easier kind of waste product to manage. But as long as we can manage the CO2 and store it in a safe and sustainable way, we believe that is the most cost-efficient way to transform natural gas into sustainable hydrogen. So that's the reason we have the tools available to manage this with steam reforming, and then it makes more sense from a commercial point of view.
Steinar, can I just introduce this? Because when I talk to developers on greenfield blue hydrogen projects, I see that they are more looking at ATR technology compared to steam reforming, because in the ATR technology, it's easier to capture the CO2. What is the main reason? Although maybe compared to a steam reformer, CapEx is a little bit higher. So therefore, I don't know how you see it, at least when it comes to new plants, that more ATR technology may be deployed finally.
We are only looking at ATR technology too. Definitely better than steam reforming. But the reason why I mentioned steam reforming has to do with the amount of hydrogen you get out of the process, and basically half of the hydrogen comes from the steam. And it's a little bit more difficult to explain it with ATR. But ATR technology is the one we use, and the reason for so is that it has all the CO2 under high pressure, so it's easy to capture almost all the CO2. With steam reforming, you only have about half of the CO2 under pressure, and then the other half needs to be captured with post-combustion, which is basically make it much more complex. It is doable, but steam reforming is the cheapest way to produce hydrogen, but if you want to capture the CO2, ATR technology is the best. So we are fully on board with your comment there.
Okay.
Thanks. Luca, congratulations on your company making a statement that it will be 50% carbon, but less emission by 2030. And I guess that's your motto also for helping your customers to do the same. Can you tell me how commercial are your turbines, the new turbines? How ready are they for the market for transporting up to 100% hydrogen?
Yeah, thank you, Barbara. And we also have a commitment in the following 10 years to go to net zero. So it's not only 50% reduction.
Wow.
Look, we are investing heavily on making the turbine capable to burn hydrogen. Is coming from hydrogen is not a new thing in industry. SMR has been there forever. The handling of the hydrogen, like Peter was saying, yes, has complication, but the industry can deal with it. We've been working with that gas for many years. The new things is that we need to unlock the utilization side as quick as the production side, because in the case of Equinor, like and other stuff, the key point is to make sure that hydrogen can be utilized as a form of power. So gas turbine is one big thing. Of course, compressors and other things. We are clearly focusing on developing combustion systems that are suitable for that. We already have experiences on some of our models. We have, of course, a very wide range of turbines. So we are taking a multi-stage steps, also in line with the blending approach that some of the companies are taking. I think we want to follow that path and work with our partners. In my presentation, I did mention about the experience we did with the SNAM. We tested a blend of 10% hydrogen in our turbine. We have a dedicated lab where we basically can do full-scale testing on hydrogen. And I think the name of the game for us, and likewise any other gas turbine manufacturer, is to make sure that the solution we found will be highly retrofittable. And I think we are on the right path. We don't want to go into plants and rebuild everything from scratch to get hydrogen to be utilized. We think we are coming up with solutions that are not very invasive and they can be very quick to be plugged in. And the other challenge and the other opportunity is that I'm strongly convinced that the journey of hydrogen and any other green fuel, it's really a cooperation journey, right? And that's why I put up that example with NAM, because I think working together with the big producer and the big utilizer of the thing is very important for the technology provider.
Yeah,
I may add in this context, Luca, I also see that we have plenty of inquiries regarding to what is the hydrogen capability of the turbines, how we can change existing turbines, and everyone wants to have it today. But then when you enter into the dialogue with the customer, you always need to ask the question, okay, what amount of hydrogen you have available in the foreseeable future that you really have fuel enough to burn? And then I think it's fair to say that everybody, you and we and the other suppliers, have much higher capabilities to burn hydrogen than hydrogen is available. And I think the technology is ahead of the supply, and therefore I have no doubt that we will have all the turbine capabilities in a few years where we have not the hydrogen to use it. So therefore, I think the main challenge is that we create a confidence in the pipeline operators that the equipment they have can be upgraded, or even if they buy something today that maybe has a certain capability, when more hydrogen is available, can be brought to whatever percentage they want. But again,
I strongly think that the blending approach is very important. So we need to follow the blending approach. We do not. It's very unlikely that the world in one day will go to 100% hydrogen in a pipeline. Right? We will go 10, 20, maybe 30, 40. So the question how we get to 100%, it's in a way it's a science question, not yet a technological question. Because in reality, like you say, there is not enough hydrogen to fill a SNAM or a Gazuni or whatever pipeline. On the other side, and I want to reconnect what Barbara said before. I don't think that the production of hydrogen would be necessarily from big bulk. So the idea of pyrolysis for me is not exclusive of the big blue hydrogen, the turquoise hydrogen, like they call it, because I think pyrolysis will have a game if hydrogen will be produced on a more distributed way. Because of course it would be more practical in smaller cluster to do pyrolysis that they do huge SMRs or other system to produce hydrogen. And I'll give it to Steinar.
So I just can give a quote. I had recently a chat with the CTO of a big steel maker in Europe. And he said to me, okay, how can I decarbonize my steel production? I need hydrogen. I need large quantity of hydrogen. At the end, I will not get it green because I just don't have not enough electricity to make it green. So my dream is I put a compact pyrolysis unit at the end of the natural gas pipeline going to my plant, make all the hydrogen I need, and disposing CO2 is for me politically much easier than disposing carbon than CO2. Of course, it's a wish.
Yeah.
So I don't know whether technology can be made available short term, whether it's economic, but I think people are looking at it from a demand side, and I know that many companies investing in technology. Whether it will fly technically, commercially in 5 years, 10 years, I don't know.
And of course, it's a balance of all the options, and it depends on your particular situation. And I think that's something that's very clear with this whole debate for decarbonization. We need all options. Steinar, did you want to add to that?
No, I was going to say exactly what you said. We need all options. We shouldn't come into a situation where we compare what is best and kind of wait for the perfect situation. We really need volume, and we need all pathways that can lead to the target. And just one comment. I mean, it was mentioned that technology exists to more or less to switch from gas to hydrogen, and for instance in power plants. And that's true. I mean, some work needs to be done to qualify the turbines, but we expect that to be solved. But the big hurdle is basically that when you switch from gas to hydrogen, you get an efficiency loss in the process of making the hydrogen, and you have all the equipment that you need to justify. Basically, the price of the electricity that you get out of this flexible power plant is more or less twice the level compared to natural gas. So what you really need is a regulation which kind of gives an economic incentive to do this switch. Because today, with the ETS that the power producers pay on the CO2 emissions, it doesn't kind of justify the switch to hydrogen. You need a higher ETS, or you need some other kind of regulation. So you really need to start there to incentivize the industry to make this switch and to make it commercial, because it's not until that point has been reached that you will see producers building these large-scale facilities of hydrogen that you need to supply the amounts required. Because the beauty of a power plant is that you have one single customer which can really take a large volume, and it is kind of a segment where you need a hydrogen solution to back up wind, for instance. You need like the flexible part of a hydrogen or natural gas fired solution. So it is an ideal kind of segment to kickstart the hydrogen economy. But what we really need is regulation which can make it also commercially attractive to make the switch.
And of course, the prime target for hydrogen is not power production. It is those areas that cannot be electrified, such as industry and heavy transport for fuel cells.
Yes, that is correct. But flexible electricity is not. That's not the same as renewable. Because renewable only produce when the wind blows and when the sun shines, and you need stored energy to produce flexible electricity to kind of fill this.
So on that note, can we talk about storage? Because Peter, you did mention storage and some of the turbines that are used to extract and from the storage. Can you comment on what is the readiness? We hear a lot of debate about the pipelines and compression. Can you update a bit more on what the status around the world for storing hydrogen? Where is it happening, and what is your sense of it?
So basically, as we discussed already, hydrogen is pumped and stored since decades. Of course, small quantity. As far as I know, the length of existing hydrogen pipeline is maybe nearly 9,000 kilometers, mainly operated by gas companies, and we have gas storage as well. Of course, small scale and high pressure tanks above ground, but as well, we have a couple of salt cover and underground storage facilities along the Gulf Coast in the US and even in the UK. And we're also in discussion with customers here in Germany and other places to convert existing gas storage facilities to hydrogen in a pilot stage, what it means for the equipment, for the capacities, and so on. And I understood from the storage companies that salt cover and storage is much better suited for hydrogen than depleted gas fields. So, and I will expect basically that it will be deployed in the near future. We need to change, of course, compressor and some other facilities above ground, but the cavern itself is available, and we have again supplied equipment for this in the US already 10-20 years back. So it's not new, but it's not deployed large scale yet.
Yeah, I know that GRT Gas has done a study, and it's available on the internet, on what is needed to convert storage and different equipment replacement parts and components at different levels of hydrogen. So it's very interesting. On the discussion of blending, Peter, why do you advise that 40% is a limit of blending, and then you should go to 100? Can you just give us a bit more? I know you mentioned it, a bit more of an overview of what where's that come from?
Basically, of course, all the pipeline operators look what we do with our installed equipment in regards to blending. And then we did studies with pipeline operators in Europe on installed equipment. And then assuming that the installed equipment is probably in average more than 20 years old, we looked at those technologies and say, okay, how it can be still used when the hydrogen plant in the gas goes up. And then from the technical point of view, the molecular weight of the gas goes down when you start blending. Okay, what can we do? And the conclusion was in those studies that basically up to 10% hydrogen in the gas, you don't need to do anything on the rotating equipment, other the turbines and the compressors. Of course, you lose some performance and you need to look at safety, but at the end, you can keep the machines as they are normally. Then between 10% and 40%, on the gas turbine side, you need to upgrade combustion, as Luca mentioned. Technology is basically available for those engines typically used in pipelines. Of course, maybe for some very old ones, they cannot be upgraded, that need to be checked individually. And for the compressor, it's more difficult because you need to increase the tip speed of the impellers to pump the lower mole weight gas more efficient. And then coming to the conclusion that if you want to keep the casing of the compressor and the auxiliaries, you can go to up to maximum 40%, but you need to increase the diameter of the impellers and increase the speed. And then when you go more than 40%, basically the casing is not sufficient, you need a new compressor. And then it's better go to 100%. But I have to say, this is a theoretical question. In case you really want to do it, you have to make an individual study on the existing equipment. The studies also show that the original assumed risk of the steel embrittlement is much less than originally thought. So it seems to be, at least you can say, basically the older the pipeline is, the more likely is it can be run with hydrogen. Very new, more high pressure systems are more vulnerable to hydrogen embrittlement. But when I talk to the pipeline companies, I think it's unlikely we reach those kind of percentages because, at least at the moment, I think they all like to say, I want to have a separate hydrogen, 100% hydrogen network to a natural gas network and only do blending when it's absolutely required. So basically saying, okay, I have to do it for small quantities because a separate line makes no sense. But I like to switch at least when I have 10% to a separate network. And we all know those plans are existing on building the hydrogen backbone, mainly using repurposing existing natural gas pipelines. So what I expect is we will see some blending to up to 10%. And then the investment requirement to do this on the rotating equipment side is small, or maybe zero, depending on how old the equipment is. And then the operators, when I consolidate what I hear from them, will switch to dedicated hydrogen pipelines, mainly using existing natural gas pipes. And then, of course, they need new rotating equipment. They may be able to contain the turbine, but definitely they need new compressors.
And Luca, can you give us a sense of what is that typical cost these days for modifications and then total replacement? We see a lot of numbers out there. Can you give us a sense of what is the expenditure?
More than the sense of the cost, I will give a sense of the size so that you get it. We're talking basically two things: modification to the combustion system and modification to some of the auxiliary system to make sure that they are hydrogen compliant on the gas turbine. On the compressor, like Peter says, there is an all rotor dynamics needs on different speed that may be needed for transporting very high content of hydrogen. I would say that it will remind the time when the pipeline had to switch from standard turbine to low NOx turbine. Similar approach. So when we went from no control on the NOx to low NOx, we had to do kind of similar stuff. So it's on the combustion level. So it's not, you don't have to do all the surrounding on the plant. It's going in terms of the proportional to the plant, it's not going to be a huge impact. And maybe Barbara, just also to echo and complement what Peter was saying. The one thing that we can be sure, consider the amount of investment and research we are doing, gas turbines and compressors are not going to be the bottleneck for hydrogen development. Actually, I think we are leading the pack. There is a lot of we accumulated so much experience on combustion, on handling hydrogen, also on the refinery side. We are investing very significant amount of capital in that respect. The blending versus not blending will most likely be driven by the rest of the infrastructure, because today the pipeline serve the complete the industrial world, the heating world. Those stuff will have a hard time to get compliant with 100% hydrogen. Hence the discussion that Peter and the point that Peter was making is very correct. If the rest of the infrastructure doesn't follow, then the gas turbine will help, but will not solve the problem.
And of course, we are seeing a lot of development in residential and commercial to 100%. I think next month there'll be 2 houses in Gateshead in England completely hydrogen ready, and you can walk through them and have a look. And there's a big campaign, of course, to get public acceptance for using hydrogen. And there's, houses in Scotland and England currently being tested. So I agree. That's maybe a longer process. Peter?
Barbara, coming back to your original question, I have heard estimations of pipeline operators estimating the cost to convert the existing pipeline to hydrogen in the magnitude of 10 to 15% of a new build. So it seems to be not very high, definitely much quicker and more economics than building a complete new infrastructure.
And if anyone in the audience is interested, the EU Backbone has a very detailed tables of what it costs to replace compression and the High Deal, the project High Deal from Spain through France and Germany, they have numbers in their report. Depending, of course, very much the highest cost component is the compression. I have a question from Heinz Wodska. I think it's for Luca and Peter, although he said it for Peter, so maybe you can answer it first, Peter. Are your gas turbines ready to run variable hydrogen content from 10 to 100% with the same burner setup? I know you talked about the impellers and casing. Is that a separate issue, or do you think
it's a separate issue? Because as Luca pointed out, on the gas turbine, you need to first adopt the combustion system in order to stay in the NOx and being ready with the different, combustion properties of natural gas and hydrogen. The highest content we are offering today, and we are just commissioning engines in this percentage, is 60% hydrogen for megawatt size as they're used in pipelines. So, of course, all the customers are asking, we have to vary. Whether finally, when we have 100% hydrogen combustors available in a few years, definitely before they have enough hydrogen, they are really economic applicable when then you switch in a day from 0 hydrogen to 100% hydrogen backwards, forwards all the time. I think there will be operational challenges we need to explore. So therefore, I would expect it's happening. It's possible technically, but I'm very sure it has performance and maybe also emission challenges we need to look at.
I agree on I think burning will find a way. Controlling emission over a wide range of changes, NOx emission will be the challenge.
And Steinar, you have a super exciting project of piping hydrogen from blue hydrogen, but hydrogen from Norway to Holland, and I know the Germans will be queuing up that as well. Do you want to comment on the business case and what you look for from the Siemens and the GEs, Baker Hughes of the world?
Yeah, so it's not really a project. It's more a study to kind of explore the potential in basically connecting to this hydrogen backbone, which has been talked about here. And what we see is that there is a lot of infrastructure going from the Groningen area into Germany and other areas, industrial areas, which will become kind of available when the Groningen field is reducing its production, and we expect this capacity to be repurposed from gas to hydrogen. So at the moment, we have lots of gas pipelines from Norway to EU, actually 7, but none of them goes into this area. So rather than repurposing one of the existing gas pipelines to hydrogen pipeline, we are considering if we could build a new one that could go directly into the kind of hub of hydrogen, which we expect to come in the Netherlands. So it is something we are exploring. Of course, this has also to do with where we kind of produce the blue hydrogen. Most of the projects that we have looked at so far has looked at producing this at the coast in continental Europe. If we locate this in Norway, it may attract industry to Norway, which is using hydrogen as kind of a feedstock. So there's a lot of strategic elements into this as well, which we are considering. It's not only a technical cost exercise that we are using.
Exactly, Steinar, because very clear when we look at the challenges to pump hydrogen through a pipe. When you fill a pipeline to the maximum of its transportation capacity and the operating pressure, you need much more compression power to do this. But if you then have a big pipe and only fill it to a certain degree of capacity, you need only some compression at the beginning, and you can bridge very long distances. Of course, this impacts the cost of the pipe versus the transportation capacity and so on. But at the end, pumping hydrogen will always be less efficient than pumping natural gas, just for the property of the molecule. So therefore, I think from the overall economics, it would be easier to pump natural gas to Netherlands or Germany, build the blue hydrogen facility at the end of the pipeline. And then, of course, if you can dispose the CO2 directly, for example, in the reservoir in the North Sea, it's easy. If you have to ship it back to Norway, it's more costly. But this needs to be considered, because I can tell you, pumping hydrogen over very long distances is very energy intensive and probably doesn't make sense.
So Steinar, we heard about that about 3 years ago. So what changed?
No, so just to respond, I fully agree that it makes more kind of commercial sense to have the hydrogen production closer to the market. But what we also need to kind of respond to is the EU hydrogen strategy, where green hydrogen very much is given priority. There is kind of a recognition that blue hydrogen will be required, but there's like a reluctance to invest in blue hydrogen value chains, kind of with kind of the concern that kind of to lock in kind of a fossil-based energy system. So this is also a response to the EU hydrogen strategy of basically importing blue hydrogen, and then from a Norwegian perspective to export it as a kind of a potential solution. So it is basically to put kind of this solution on the table as one alternative to producing the blue hydrogen in continental Europe, and then manage the CO2 from there. Either store it locally offshore, or pipe it back to Norway for permanent storage of the Norwegian coast. So it's basically exploring the option space. That's what we do.
So Steinar, with so much renewable energy in Norway, how much focus are you putting on delivering green hydrogen and just avoiding all the issues with blue hydrogen?
So it's if we kind of continue on this kind of solution of looking at the large-scale hydrogen production in Norway in a pipeline to Europe. To justify a pipeline, we would need something like close to 100 terawatt hours of hydrogen, talking about 10, maybe 12 gigawatt. If we were to produce that with green hydrogen, it would actually consume the entire Norwegian hydropower capacity. That's of course not feasible at all. But it would only consume 10% of what we export as natural gas to Europe today. That's much more feasible. So we believe that we can start this on a blue basis, get the infrastructure in place, and then we can add a green hydrogen over time, more and more, as we will develop offshore wind and other kind of sources of renewable electricity. So blue hydrogen has the muscle to kind of lift this, and then over time we can scale in more and more green. That is like the division, if you like. We will not be able to lift this with a pipeline based on green hydrogen in the near term.
In the short term, yeah.
No.
Yeah. So for Luca and Peter, can you talk about the demand for your hydrogen-ready equipment around the world? Where do you see, maybe Luca first, where do you see the demand? What parts of the world are looking at it mostly?
Look, I think the hydrogen-ready equipment is now very much looking at project, especially around the green ammonia production. I think the biggest one. I see a lot of projects going on in Australia. Of course, there are very famous projects going on in Middle East. There is demand from this side. It's on the both on the production side of hydrogen for the more sophisticated compressor, but also on the spinning reserve for gas turbine that are used, of course, to burn hydrogen to allow for the storage, for the chemical storage that I think Peter was alluding to before. So those two are very, very active in terms of mega projects. And then, of course, there is all this interaction with the different user of our equipment that are starting to plan for decarbonize their operation, and this is pretty much everywhere.
So I can basically confirm that we see the first inquiries from Australia where a lot of photovoltaic-based hydrogen production is considered. And then, of course, again, how to bring the hydrogen to Europe or other markets. And then they look at green ammonia or other solutions. What I hear, it's unlikely they use liquefied hydrogen because it's very energy intensive. Again, of course, center of the interest is Europe at the moment, but we see upcoming projects in China. And last not least, I have to say, I really see a very steep increase since, I would say, 2-3 months in the US, where really companies that in the past we know being developer maybe for LNG or other natural gas-based facilities, now now I need to look at blue ammonia or green ammonia or whatever, because they have the same problem, how I bring the hydrogen I produce to the market. And clear as liquefaction is not available large scale, piping is not possible over the long distance. So I think the ammonia, whether it's green or blue, doesn't matter, is at the moment I see a lot of focus on that. This is probably becoming the hydrogen energy carrier in vessels over long distances, and it's currently piloted in the Middle East as well.
Yeah. We have 8 minutes left. Can we talk briefly, please, about policy and the role of policy in you being able to do your job? And I guess that's more relevant for Steinar, where you are, you'll be seeking approval for these projects and possibly reacting to pressure from the government to be part of the solution. Can you, first, Steinar, can you comment on what are you asking for from policymakers, or do you have it in Norway at the moment?
Well, Norway is one thing, but the most important market for us is Europe and EU. That's where we sell, and 99% of the gas we produce in Norway is exported out of the country. So the EU energy policy is by far the most important for us, because that's our market. And what we see is very strong commitment. First of all, to move to a zero carbon energy system. That's really good. But also to back this up with policies. So what we are really kind of focused on and asking for is a level playing field, in particular between the different colors of hydrogen, not the gray one, but those that are sustainable in terms of no CO2 emissions. That's important, and it's important in the context of getting sufficient volume. We are confident that, for instance, the blue hydrogen will be required to get the scale that we need. So just one example is kind of the EU hydrogen strategy with the 40 + 40 gigawatt, which is really aggressive and forward-leaning, really welcoming that. But the natural gas market in Europe is 500. And basically, we can replace natural gas with hydrogen in most appliances. We can also switch out coal and use hydrogen in steel manufacturing. So the market is even bigger than the 40 + 40, much bigger.
Yeah.
And in that context, we need kind of policy also for blue hydrogen. And important here is also that we need to look at this from an industrial perspective. That if we get kind of large amounts of clean energy, it will also stimulate kind of attracting industry to Europe and not have them flag out. And this is important because you need to balance all the costs with creating jobs. So we need to look at this with kind of a mindset where we look at opportunities as part of this journey towards a zero carbon energy system. And then we believe kind of fossil-based like the blue hydrogen system is really important to get the scale and at an acceptable cost.
And Peter, from Siemens' point of view, what do you ask policymakers as the manufacturer of equipment, not the producer of the gas?
Okay, I can only basically confirm what Steinar said. We need, on one hand, basically the economic and regulatory environment that hydrogen is really deployed. That means CO2 tax, incentives, cost, whatever. Otherwise, the project will not fly. And then there's one key element of this, in particular for the blue, it means the final storage of the CO2 in the ground. As there are only a few companies where currently already regulations and laws are available, and Norway is one of them, that you really are allowed to put it in. And although it's regulated, who is take the final risk that the CO2 stays in the ground forever? The similar discussion, similar like maybe nuclear waste, of course, less risky. And even when I talk to investors in the US that looks at this, they say, okay, I cannot take this risk if it's not regulated by law from the federal government, it will not fly. And therefore something needs to happen. But I'm optimistic on it because even in Germany, where we had this very negative discussion on carbon storage, CO2 storage some years back when they had a coal-fired discussion, now the government realizes, okay, even independent from blue hydrogen, I have to capture huge quantities of CO2 from other industries and I need to dispose it somewhere. So therefore, it seems to be really that even in Germany, they are looking at it and considering, and the public discussion has started to allow CO2 storage in reservoirs or aquifers, particularly in the German offshore part of the North Sea, not so much onshore. But this was a discussion that was not even, I couldn't imagine to happen a couple of months ago. But now they realize it has to happen because we have to find a way to dispose of it. We cannot ship everything to Norway. Because we talk about at the end, we finally, I had to estimate in 2035 already, the world needs to capture and store 3 gigaton of CO2. And today, I think the overall carbon capture and storage capacity globally is 50 megaton.
Yeah.
This is a very big challenge.
Thank you, Peter. Luca, you have 1.5 minutes.
I had a blink on my Wi-Fi. Very quickly.
That's okay. You're back, which is great. What is your company?
An analogy on the policy question is very important. 15 years ago, there was not a single wind project that was commercial without subsidies. Subsidies came in, scale was get, and now the people can make money on project. Same thing has to happen on hydrogen and also on CCUS. So there's a lot of decisions that the world will need to take, starting from Glasgow in November. I think we need to run the same journey and allow for all the additional fuels to be part of this energy mix. And without policy support, system and cooperation is not going to happen.
Yeah. So it is very important. So I would, with that, unless anyone has a final word to say, we have 1 minute. Would anyone like to make a final statement? Or I will thank you all for a lively discussion and a very honest discussion and some very key points. And again, as I said at the beginning, I think you within your companies, you are leaders, and thank you for your work. And we look forward to seeing more development and more positive trends towards renewable energy being transported as a gas to increase the uptake of renewable energy and be part of the decarbonization. So thank you. And thank you for your time today on the panel. So thank you. We will return back to Dennis at the PDC conference, and thank you, Dennis, for inviting us all to talk. And I'll close the panel session.